Whoa. Nice work. Alright, what I'm going to try and do is summarise all of level 2 mechanics in one short video. So there's a few things that we're going to start with. Before we can really talk about mechanics, I think we need to look at a couple of different terms. One of those is a scalar, and another one is a vector. So a scalar is any quantity that only has magnitude. So it only has a value, is basically what that means. There's lots of different examples of this. You've got mass, energy, distance, and you've got speed. These are all examples of scalars. They only have a value. Then there's vectors. Vectors have magnitude and they have a direction. So some examples of this are displacement, velocity, force, and momentum. So vectors are often shown with an arrow because they have a magnitude, which is represented by the size of the vector, the length of the arrow, as well as a direction, which is the direction that the arrow is pointing in. These all make sense if you say that you have, say, a velocity in a certain direction. Where down here with magnitude, if I said I had mass, 80 kgs of mass east, it wouldn't really make sense. So scalars and vectors are really important things to understand in terms of mechanics. And we're mainly going to be focusing on these vector quantities, and I'm going to link together 4 vector quantities in this next diagram here. So when we're discussing the motion of objects, there's these 4 things that we really need to consider. The first one is displacement, which is kind of like distance in a way, but it's a vector quantity of distance. If you have 2 points, A and B, there's lots of different paths you could take between A and B. This is one valid path you could take from A to B, but the displacement from point A to B is always going to be the same. It's always a straight line from A to B, as if you've got a helicopter, for example. So this distance is in pink and the displacement is in orange here. The other thing you can have is velocity. Velocity is like speed, but again it's a vector quantity, so it has a direction as well. Its velocity is in meters per second. My v's often look like square roots. And these two things are linked together. If an object has velocity, it means its displacement is changing over time. So velocity is equal to change in displacement over time. So then the next thing up here is what happens if velocity is changing over time. If something's velocity is changing over time, it has acceleration. Acceleration has the symbol A and is measured in meters per second squared. And the equation for that is change in velocity over time. The last thing we need to look at here, the 4th thing on this scale, we'll get to in a moment. I just want to look at these graphs over here before we get to this. Whenever you're describing the motion of an object, you should be talking about the object's displacement, its velocity and acceleration, and how they might be changing over time. Another way you can do that is through a graph. So here I'm going to graph an object's motion, and I'm going to divide it up into a few different sections. And those sections correspond to the same positions on these graphs up here. So this bottom graph is a displacement time graph, and it shows if you imagine you're standing at some point and you're observing an object, say you're standing here and there's a person in a motor vehicle next to you, and you're looking at the displacement between you and the motor vehicle over time. And here what's happening is the motor vehicle is getting further and further away from the observer over time. At the end here, the distance between the motor vehicle and the observer doesn't change. So this is a displacement time graph. Up here we've got a corresponding velocity time graph for this. So you can see here that the gradient of this line is increasing. And on a velocity time graph, So on a displacement time graph, the gradient is equal to the velocity. The reason for that, to work out the gradient of a line, and let's take the straight line section here, you do work out the gradient of this line by doing rise over run. On the rising axis we have displacement. If you divide that by time on the running axis, you get d over t, which is how you calculate velocity. So the gradient here is the velocity. Over here, if we look at the gradient is slowly increasing over time, which means that the velocity on the velocity time graph must also be increasing over time. In this section here, we have a constant gradient, which means we must have a constant velocity. So on the velocity time graph, for the same motion, you get a flat line section here. In this section here, the gradient is getting less over time, which means the velocity must be getting less over time. So the line comes down like this. And then finally, in this last section, the displacement is not changing, or the gradient is equal to 0 in the displacement time graph, which means the velocity must be 0. On a velocity time graph, this time, the gradient is equal to the acceleration. And the reason for that is the same as why the velocity is the gradient of a displacement time graph. Because over here, the acceleration is equal to the change in velocity over time, the gradient is equal to the rise over run. And on the rising axis we have velocity, and on the running axis we have time. Another interesting thing on a velocity time graph is the area under the line. The area under the line also represents something, and those people that are good at calculus will already know where I'm going with this. To calculate the area under the line, let's just take this rectangular section in here. The way you do that is by doing base times height. So that means we'd get t times v, or you can rearrange that, v times t. And if we look at this equation down here, v equals d over t, I can rearrange that to get d equals vt. And remember, to work out the area of this rectangle, it's velocity, rise, height, times time, which is the base. So the area of a velocity time graph is actually the displacement. And then we can go up to this top graph, which is the acceleration. So we've already mentioned down here that the gradient is the acceleration. Here we have a positive gradient, which is constant, which means we have constant acceleration. Here we have no gradient, so we have no acceleration. And here we have a negative gradient, which means we have a negative acceleration. And then the final section here, we have no gradient, so we have no acceleration. So you can always link these three different types of graph together, and on the acceleration time graph up here, the area under the acceleration time graph is equal to the velocity. Okay, so let's come back to this diagram here. We've got displacement, velocity and acceleration. Then there's this other thing up here. Velocity is a changing displacement over time. Acceleration is a changing velocity over time. This top box is about what causes acceleration. And the thing that causes acceleration is a force. In particular, it needs to be an unbalanced force. Whoopsie. And forces are measured in newtons after Isaac Newton. And this is actually how much acceleration you get for a known unbalanced force is one of Newton's 3 laws. Newton's first law is a bit wordy. It goes something like this. If the forces of an object are balanced, it will travel at a constant velocity. Newton's second law is the opposite of this. unbalanced forces cause acceleration, and it has the equation F equals ma. The larger the force on an object, the more it will accelerate.
Where are you going?
And Newton's third law is probably the most misunderstood, but one that most people could probably quote. For every action there is an equal and opposite reaction, which means if one object is pushing on another, the other object is pushing back with exactly the same force, and this is always the case.
Go. When you're ready, let it go. Go safe. Touch it. Jump.
Okay, so to understand Newton's laws, we need to understand a few things, like how do you work out if the forces on an object are balanced? And one way to do that is to work out the total or the net force on an object. To work out a total, you always add things together, and we need to consider when we're adding vectors together not just the magnitude but also the direction of those vectors. So say we had two forces acting on an object, force A and force B. We can add them together like this. You can draw the first force, you can draw the second force on the object, and then the total force is from the first tail to the last head. F total. Now we can't just simply add A to B because that doesn't take into account the direction. We need to add vectors like this where we consider their direction, which means to find the total force here, we actually need to use Pythagoras. Another thing you might be asked to do is to find out the difference, or another way that might be described is the change in for example, you might be an avid cricket player with your racket, your cricket wicket, and you might have a ball coming in with some sort of initial velocity to your bat, and it comes off your bat in a different direction and with a different velocity. And you might be asked to work out the change in or the difference in these two velocities. To work out the change in anything, in this case velocity, the way we do that, as always, the final velocity minus the initial velocity. And we need to consider these values as vectors. So the final velocity is a vector in this direction, and the initial velocity is a vector in this direction. So we can't really subtract vectors, but we can add vectors together. So the way we overcome this subtraction issue here is with a bit of maths trickery. We're going to add together the negative of the initial velocity. What that means is that we're just going to flip around the direction of the initial velocity. So the final velocity is still in this direction here, but the initial velocity, I'm going to add it in this direction, like so. So if I drew a vector diagram of this, I would start with the final, and I would add to it the negative of the initial. So I'm trying to draw these vectors as the same size and in the same directions, the VF vectors and the VI vectors, but I've flipped the direction of the VI because it's the negative value. And again, the resultant vector is from the first tail to the last head of my vector diagram, and this is the change in velocity here. We're often asked to work out the change in velocity if we're working out, for example, acceleration down here, and also for momentum, which we'll cover later on. In terms of level 2 and 3 physics, we're always going to be dealing with some form of right angle triangle, so that we can use either Pythagoras or trigonometry to work out the lengths of these sides. With a total vector diagram, another thing we can think about is components of, in this case, a force. But often we would look at the components of a velocity. We might want to break something like this force down into two components, a horizontal component and a vertical component. So if we know the total value and the angle in here, we can use trigonometry to work out the magnitude of these two sides. And knowing the components of velocities is a really important thing to understand for projectile motion. Projectile motion is the one type of motion that we need to consider in level 2 physics that uses these four concepts down here, Newton's laws and vectors, to describe it. It also uses these things called kinematic equations, which I'm not going to go into in this video. So for projectile motion, any object that's thrown into the air is described as a projectile. And the simple condition for an object to be a projectile is that the only force acting on it is the weight force. Now, because the weight force is acting vertically downwards always, this means two things for projectile motion. Firstly, it means it's accelerating down at a constant rate, because the only force is acting downwards is only affecting the vertical velocity of the object. Because that force is constant and the mass of the object is constant, then the acceleration is also constant. And when we consider the horizontal frame of reference, the horizontal velocity remains constant. The reason for this is that there are no horizontal forces acting, so there is no acceleration horizontally, so the velocity must remain constant. The other type of motion we need to consider at level 2 is circular motion. In circular motion, that's when an object is travelling in a circle. If an object is travelling in a circle at a constant speed, the direction that it's travelling is still changing, which means even though it can be going around at a constant speed, its velocity is constantly changing. And if an object's velocity is constantly changing, that means it must be accelerating. And for acceleration to occur, there must be some sort of unbalanced force, and it's called centripetal force. If for some reason whatever's providing the force to the object travelling in circular motion disappears, then the object will travel off at a tangent to the circle, because if there's no force, then you have constant velocity, which means the velocity will no longer change. A common example of this would be spinning a ball around your head on a string, and if that string breaks, the ball will travel off at a tangent to that circle. Another thing we can consider when we're looking at forces is torques. So mouth, get it? Talks. Now, talks are about rotating objects. If you have forces that are acting at a distance from some sort of pivot point, those forces act to try and rotate the object, in this case a seesaw. This force on this side is trying to rotate the seesaw in this direction, and this force on this side is trying to rotate the seesaw in this direction. Both of these forces are creating what is called a torque, and a torque is equal to force times the right angle displacement from the pivot point. So this here would be D2, so the distance to object 2, to this boy here, and this one here is D1, the horizontal distance or the right angle distance to object 1, this girl here. You'll notice that this displacement and this force are at right angles to each other, and there's the same case on this side. This object is creating an anti-clockwise torque, and this object is creating a clockwise torque. If these two torques are balanced, then the object will... It's tricky what I need to say here. I would say it would balance, and this year in level 3 physics we would say that it has constant angular velocity. Okay, we're almost finished, and there's just a couple of last things to cover off. This one here is a pretty big one. It's energy. Energy has the symbol E, and it's measured in joules. Now there's a certain amount of energy in our universe, and that energy, the amount of energy, does not change. And energy is the ability to do work. We'll explain what work is soon. There's lots of different types of energy. For example, an object that gains height gains gravitational potential energy, or EGP. An object that's moving has kinetic energy, or EK. And a mass on a spring, for example, that stretches the spring has elastic potential energy, EEP. There's lots of other different types of energy, but these same laws that I'm about to write apply to all different types of energy. So you can't create energy, you can't destroy energy, you can only transfer, which means take it from one object and give it to another, or transform energy, which means taking it from one type and transferring it to another. For example, lifting up a ball and dropping it will convert gravitational potential energy into kinetic energy. Now, this isn't 100% true. If you do modern physics, you'll understand what I'm talking about here. But for level 2 mechanics, you can assume that this is the case. So, work. Work is shown as delta E, also W. It has the units of joules as well, just like energy. Technically what work is, if you apply a force to an object, like if you're pushing a box across the floor, if you apply a force to an object over a certain distance, you are doing work. The force times the distance is equal to the amount of work that is done. Now this force times distance is different to this force times distance down here. This is talking about right angles and torques. This is talking about forces that are acting in the same direction as the displacement. Another way to think about work, which I find a bit more intuitive, is that work is simply the amount of energy transformed. So power is how quickly energy is transformed, or how quickly work is done. So the last concept to cover is momentum. Momentum is like the amount of movement, or amount of motion an object has. Now, momentum has the symbol P, is equal to mass times velocity, which means it has the units kg meters per second. So the total momentum is conserved in collisions and explosions if there's no external forces acting. So for example, down here, if we had a car that was stationary at a traffic light and a car came from behind and it was moving, this car has momentum and this stationary car has no momentum. If they crash into one another and this car comes off backwards, then this car must gain momentum in the opposite direction, and it must gain enough extra momentum so that the total momentum here is equal to the total momentum here. And the final thing to consider with momentum is impulse. Impulse is the change in momentum. The change in momentum is also equal to the force on an object times the time that that force is acting. So for example, in a collision like this, the time of the collision is t. And in collisions, if you don't want them to be painful, then they need to take more time. If the collisions take more time, then there's less force, and the force is what causes the pain in a collision. So that's why modern cars have a whole lot of safety features like airbags to increase the time of collisions and decrease the force on the occupants in cars when collisions occur. So that's all of level 2 mechanics on one piece of paper. Ran out a little bit of space at the top here, but hopefully that is a thorough enough summary for us to get on to some level 3 physics, where we're going to focus on a lot more on this torque stuff, and we're going to build on all these ideas here. We're going to look at a few different types of motion. We're going to look at another type, which is rotational motion, which comes out of these torque things. We're going to look more at momentum, but we're going to look at momentum in 2 dimensions instead of just in 1 dimension. And we're going to look at circular motion some more. What happens though if we go around circles on banked corners? And we're going to look at another type of motion, which is called simple harmonic motion, which is like a mass when it bounces on a spring, which, kind of like projectile motion, has a really simple condition that must be true for an object to be in simple harmonic motion. Alright, hope that was helpful. Cheers.